Section 5.7 is on roots and zeros. So given the following polynomial function, f of x equals x to the fourth plus 2x cubed minus 7x squared minus 8x plus 12, all of the following things are true. The zeros of the function are -3, -2, 1, and 2. The roots of the equation, that is when f of x equals 0, are -3, -2, 1, and 2. The factors of the polynomial are x plus 3, x plus 2, x minus 1, and x minus 2. And the x-intercepts of the graph are -3, 0, -2, 0, 1, 0, and 2, 0. And these are all related. To be honest, it's really like 4 different ways of saying the same thing. Let's take a quick look at the graph of this function, see what it looks like. So here I've put it into my calculator. And when I hit graph, I get something like this. I changed the window a little bit so we could see where it crosses the x-axis a little better. We're not going to see the relative max that's kind of up here above, okay? But you can see that it crosses the x-axis at -3, -2, 1, and 2. And that's what I said all of these numbers were based on. The zeros and the roots, so the zeros of the function and the roots of the equation are -3, -2, 1, and 2. And as you saw from the graph, that's where it crosses the x-axis. Also, those are the x-intercepts. Now, the factors are what you get when you do x minus each one of those numbers. So x minus a -3 is x plus 3. X minus a -2 is x plus 2. X minus 1, okay, is x minus 1, and x minus 2 is x minus 2. So all of those numbers are related to each other. So the fundamental theorem of algebra, sounds really important, doesn't it? Says that all polynomial equations with a degree greater than 0 have at least one root in the set of complex numbers. And the corollary to that is that a polynomial equation of degree n has exactly n roots in the set of complex numbers, including repeated roots. So let's take a look at a couple examples here. We're going to solve each equation and state the number and type of roots. So solving this equation, it doesn't really look factorable to me. Maybe it is, but remember the surefire way to solve any quadratic equation, and this is quadratic since it has an x squared, is to use the quadratic formula. So x is equal to -b plus or minus the square root of b squared minus 4 times a times c all over 2a, or x equals 5 plus or minus the square root of -87 over 4, and 87 might be factorable, but I don't think there's anything that's going to be able to come out of there. So x is equal to 5 plus or minus, taking that -1 out, I square root of 87 over 4. That's the solution to this equation, and it has 2 roots because it's an x squared, and the 2 roots are imaginary. So it has 2 imaginary roots. Okay, let's take a look at another example. 8x cubed minus 27 equals 0. This is going to be a difference of 2 cubes, and in this case a is going to be equal to 2x, because 2x, the quantity 2x cubed is 8x cubed, and b is going to be 3. So plugging that into the formula, a minus b times a squared, which is 4x squared, time, let's see, so this is going to be plus a times b, and then plus b squared. That equals 0. So one of my solutions, 2x minus 3 equals 0. So x is going to be equal to 3/2. There's one solution. And then 4x squared plus 6x plus 9 equals 0. That cannot be factored, so I do need to use the quadratic formula on that. X equals -b plus or minus the square root of b squared minus 4 times a times c all over 2a simplifies to negative 6 plus or minus the square root of negative 108 over 8. That simplifies to negative 6 plus or minus 6i square root of 3 over 8, and then dividing all of my coefficients by 2. X equals negative 3 plus or minus 3i square root of 3 over 4. There's my other solution. So I have a total of 3 solutions, 1 real, 2 of them complex, and that makes sense because I have my original equation is an x cubed. So I have 1 real solution and 2 complex or imaginary solutions. So in order to find all of the zeros of a function, we're going to graph the function to find one real zero. So we're going to graph it to find one place where it crosses the x-axis, then we're going to use synthetic substitution or synthetic division to factor and to find the other solutions. So here's our first example. Find all of the zeros of f of x equals x cubed minus x squared plus 2x plus 4. So I don't know what a zero is, so I'm going to go ahead and graph that. So let's going back to our calculator. I have x cubed minus x squared plus 2x plus 4. Let's see, I probably need to zoom back out to a standard window. And looking at the graph of this, oh my goodness. Well, it looks like I have, it only crosses the x-axis in one spot. It looks like it's negative 1. I think I'll confirm that by going to the table. Let's go to the table. Let's put, actually I have negative 1 in there. It's actually my second number already. So when x is negative 1, y is 0. So yes, I do have one real zero at x equals negative 1. So from the graph, I got that x equals negative 1. So there's one real zero. So let's use that in synthetic substitution or synthetic division. List the coefficients, 1, negative 1, 2, and 4. Draw your line, bring down the first coefficient. Negative 1 times 1 is negative 1. Add those, negative 2. Negative 1 times negative 2 is positive 2. Add those, 4. Negative 1 times 4 is negative 4. And I have a remainder of 0. So that means these are the coefficients of a polynomial that starts with an x squared. So this is going to be x squared minus 2x plus 4. Okay, so that equals 0 because I need to find the zeros. I already have one right here. One of my zeros is negative 1, but now I need to figure out what zeros I have here. I don't think this is factorable, so I'm going to use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a, or 2 plus or minus the square root of negative 12 over 2 plus or minus 2i square root of 3 over 2, and canceling, that gives me x equals 1 plus or minus I square root of 3. So I have one real solution at x equals negative 1. I have two imaginary or complex solutions at 1 plus or minus I square root of 3. And then actually looking back at the graph, that makes sense. There's only one real solution, and because that's the only place it crosses the x-axis, it makes sense that there would be two complex solutions. Let's try another one here. So here I have f of x equals x to the fourth plus 6x cubed plus 73x squared plus 384x plus 576. Oh my gosh. Let's graph this on the calculator to find one real solution. So let's clear that out. I have x to the fourth plus 6x cubed plus 73x squared plus 384x plus 576. Okay, let's see what the graph of that looks like. Whoa. Okay, well, let's see. It looks like it crosses, or it touches the x-axis right here at x equals -3. Let me go to my table and make sure that that's true. Let me put in -3. So when x is -3, y is indeed 0. So I do have one real solution at x equals -3. And in fact, because the graph looks like this, because it doesn't actually cross and it touches, I know from graphing quadratic functions before that that's actually going to be a repeated root. So x equals -3 twice. So I know that one factor, or one solution, is x equals -3. Let's use that in synthetic substitution. So -3 and 1, 6, 73, 384, and 576. Bring down the 1. It's going to give me -3, 3, 9, oh wait, -9, 64, -192, that leaves me with 192, and then multiplying that gives me -576, and a remainder of 0. So that means that this other factor is x cubed plus 3x squared plus 64x plus 192. And I don't really want to try any other way to factor that. Because I knew that x equals -3 was a repeated root, I'm going to go ahead and use that again. And this time I'll use the coefficients of my solution that I got here. So 1, 3, 64, whoops, move those closer together, 64 and 192. And then we'll do synthetic division again. -3, 0, 3, or 0, 64, and -192. My solution is 0. This turns into, since I started with an x cubed, this is going to be an x squared, so x squared plus 64, and that equals 0. So let me move that up here just to get it out of the way a little bit. Solving that, x squared plus 64 equals 0. X squared equals a -64. Taking the square root of both sides, x equals plus or minus the square root of -64, or that's going to be x equals plus or minus 8i. So all of my roots are x is equal to -3, and that was actually a repeated root, so I'll list that twice, a positive 8i and a negative 8i. And it makes sense that I should have 4 solutions because it started out as an x to the fourth. The complex conjugate theorem says that if a polynomial has a 0 at a plus bi, then it also has one at a minus bi. So if a polynomial function has a 0 at a complex number with a plus in there, there's also going to be a -1 as well. So if you are given the zeros of a polynomial function, so in other words, if I were given these answers right here that I boxed, I can work backwards and come up with the function itself. So let's do that in these examples here. So write a polynomial function of the least degree with integral coefficients, so in other words, the coefficients are not going to be fractions, they have to be whole numbers, that has the given zeros. So we have negative 3, 1, and negative 3i. And according to the complex conjugate theorems, if negative 3i is one of the zeros, it also has a 0 at positive 3i. So what does this mean? This means that x equals negative 3, x equals 1, x equals negative 3i, and x equals 3i. So let's make each one of those equal to 0. So adding 3 on both sides. X plus 3 equals 0, x minus 1 equals 0, x plus 3i equals 0, and x minus 3i equals 0. So these are actually the factors of the polynomial function we're looking for. X plus 3 is a factor, x minus 1 is a factor, x plus 3i is a factor, as is x minus 3i. So I can say that the polynomial, the function I'm looking for, is equal to x plus 3 times x minus 1 times x plus 3i times x minus 3i. So all I have to do is multiply that out and come up with my function. So this right here, if I were to FOIL this, I'm going to get x squared plus 2x minus 3. And if I were to FOIL these guys right here, I'm going to get x squared. Now let's think about this. 3i times x and x times negative 3i are going to cancel each other out, because this is going to be a positive 3i and x, and this is going to give me a negative 3i and x. So really all I have to worry about is 3i times negative 3i. That's going to give me a negative 9 times I squared. I squared is negative 1. Negative 9 times negative 1 is a positive 9. So now I have these two factors that I need to multiply out. And I think I'll start by taking this x squared and multiplying it by each term of this trinomial. So that's x to the 4th plus 2x cubed minus 3x squared. Now 9 times each one of these, plus 9x squared plus 18x minus 27. Cleaning that all up, I'll have x to the 4th plus 2x cubed plus 6x squared plus 18x minus 24. So the function of least degree that has negative 3, 1, and negative and positive 3i as its zeros is this function right here. So it's basically just doing what we've been doing backwards. And let's take a look at one more example here. So the zeros are negative 2, negative 3, and 4 minus 3i, but that means I can also add 4 plus 3i, also as a 0. So if x equals negative 2, x equals negative 3, x equals 4 minus 3i, and x equals 4 plus 3i. Let's set each one of those equal to 0 to come up with our factors. So x plus 2, x plus 3, and this is going to be x minus 4 plus 3i. So that's subtracting 4 from each side and adding 3i to both sides, and x minus 4 minus 3i. So my function is going to equal x plus 2 times x plus 3 times x minus 4 plus 3i times x minus 4 minus 3i. Okay, so let's do the easy one first. I'm going to FOIL these, and that's going to give me x squared plus 5x plus 6. Now this one gets a little complicated because I need to treat it as though I'm multiplying a trinomial times a trinomial. So I think I'll start with this x and distribute it to each term here. So that's going to give me an x squared minus 4x minus 3xi. Okay, now I'll distribute this negative 4x plus 16 plus 12i. And now let's distribute this 3i. So that's going to give me a plus 3xi minus 12i. And then that's going to give me 3i times negative 3i is going to give me a negative 9 times a negative 1, or plus 9. Now, I have a feeling I've got some stuff in here I can cancel out. In fact, I have a negative 3xi and a positive 3xi, and a positive 12i and a negative 12i, and did that make all of my i's cancel out? I believe it did. So now I'm going to have x squared, let's see, minus 8x, and 16 and 9 plus 25. Okay, so now I have this factor here, x squared plus 5x plus 6, and then x squared minus 8x plus 25, and that's what f of x is going to equal. So again, I need to multiply all of that out. Let me give myself a little extra room here. So I'll take this x squared and multiply it by each one of those. X to the 4th minus 8x cubed plus 25x. 5x times each one of those, plus 5x cubed minus 40x squared plus 125x, and now 6 times each one of those, plus 6x squared minus 48x plus 150. Let me check my notes and make sure I got that right. It's very easy to make a mistake when you're doing all of these. Okay, so let's clean that up. So f of x equals x to the 4th, and what do I have for cubes? Minus 3x cubed. Let's find our squareds. Oh, actually this one was supposed to be a squared. Is that right? Yep, 25x squared. X squared, so that's going to give me a negative 15 plus 6 gives me a negative 9x squared. And my plain old x's, I subtract there, that's going to give me a positive 77x and plus 150. So that is the polynomial that has negative 2, negative 3, and 4 plus or minus 3i as its roots.